Good evening. In the last lecture, we started this topic, method of induction. So in method of induction, the result which we have to prove, we denote it by P of n. Then we verify that P of 1 is true. By assuming P of k is true, we prove that P of k plus 1 is true. And therefore, by method of induction, we say that the result is for all small n belonging to capital N. Now, exercise 4.1, question is the same, that using method of induction, prove the following for n belonging to capital N. Ninth one, 1 upon 3 into 5. I hope you won't treat it as decimal point. So 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 to n terms is n upon 3 into 2n plus 3. So this we have to prove. We denote it by P of n. Now degree of difficulty is increased because we do not know nth term. So the main job is to find nth term. You will observe that each denominator is product of two numbers. What are the first numbers in the products? 3, 5, 7. These are in AP with first term 3 and common difference 2. So the first number in nth product will be what? A plus n minus 1 into d, that is 2n plus 1. Similarly, we'll do that orally and then we'll write 5, 7, 9 are again in AP. First term 5, common difference 2. So the second number in nth denominator is 5 plus n minus 1 into 2, that is 2n. It will be what? 5 plus n minus 1 into 2. So 5 plus 2n minus 2, that is it is 2n plus 3. So what is the nth term? 1 upon 2n plus 1 into 2n plus 3. Right up. So what is P of n? 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 up to 1 upon 2n plus 1 into 2n plus 3 equal to n upon 3 into 2n plus 3, where n is a natural number. Now, in the first step, we verify that P of 1 is true. So, for n equal to 1, what is LHS? N equal to 1 means first term. So, you can put n equal to 1 in nth term, or this is the first term. So, 1 upon 3 into 5, that is 1 upon 15. What about RHS? 1 upon 3 into 2 plus 3, that is same 1 upon 15. So, LHS equal to RHS. This means P of 1 is true. Now in the second step, we assume that result is true for some k, which is again a natural number, that is P of k is true. Means what? 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 up to 1 upon 2k plus 1 into 2k plus 3 is what? K upon 3 into 2k plus 3. This is number 1 because we have to make use of this. In the third step, we prove that P of k plus 1 is true. Please listen to me. What do you mean by P of k? Basically, k terms. So what is P of k plus 1? K plus 1 terms. So on left hand side, we write these terms. So I have written these k terms, and the next term is obtained by replacing k by k plus 1. Here I have omitted one step. I have directly written this. I'll explain that. See, k is to be replaced by k plus 1. So 2 times k plus 1, that is 2k plus 2, because when you open the bracket, so it is 2 into 1 also. So 2k plus 2 plus 1, so 2k plus 3. Here 2 into in bracket k plus 1 plus 3. So 2k plus 2 plus 3, so 2k plus 5. I hope this is clear now. On right hand side also, replace k by k plus 1. So it is k plus 1 upon 3 into, previously it was 2 times k, now it is 2 times k plus 1, that is 2k plus 2 plus 3, that is 2k plus 5. So we have to prove this. We begin with LHS and we show that LHS is same as RHS. So this is LHS. Now see the cursor. Sum of these terms is this from 1. So 1 term extra. How do we add fractions? LCM. LCM is 3 into 2k plus 3 into 2k plus 5. Numerator k into 2k plus 5 plus 3. That is 2k square plus 5k plus 3. What are the factors? K plus 1, 2k plus 3. 2k plus 3 gets cancelled. So k plus 1 upon 3 into 2k plus 5, which is nothing but right hand side. This means P of k plus 1 is true. You need not write this in exam, but this means P of k is true implies P of k plus 1. Okay. Then in the last step, from above, means from above 3 steps, and by principle of induction, by principle of mathematical induction, P of n is true. This is inverted A for all small n belonging to capital N. For convenience, we have written P of n. So you have to write original. That is 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 to n terms, up to n terms, is nothing but n upon 3 into 2n plus 3, where n is a natural number. Sum number 10, using induction, we have to prove that 2 raised to 3n minus 1 is divisible by 7. See, we say that 15 is divisible by 3. Means what? 15 is an integral multiple of 3. So 2 raised to 3n minus 1 is divisible by 7. IFF is the standard short form of if and only if. This is standard short form of if and only if. So 2 raised to 3n minus 1 is divisible by 7 if and only if it is multiple of 7. So let Pn be 2 raised to 3n minus 1 equal to 7m, where m is natural number. Because 15 is 15 by 11 into 11. But we don't say 15 is a multiple of 11, right? So when I say this is multiple of 7, so it is 7m, where m is a natural number. Now, first step, for n equal to 1, we get 8 minus 1, that is 7. Is 7 divisible by 7? Yes. So P of 1 is true. Second step, we assume that P of k is true. That is 2 raised to 3n minus 2 raised to 3k minus 1 is divisible by 7. So let it be 7a, where a is a natural number. So rearrange the terms. So what is 2 raised to 3k? It is 7a plus 1. We have to make use of this. So this is second step. Now step 3, we have to prove that P of k plus 1 is true. That is to prove 2 raised to 3 into in bracket. You have to use bracket. Otherwise, if you say 2 raised to 3k plus 1, that is wrong. Previously, it was 2 raised to 3k. Now it is 2 raised to 3 into in bracket k plus 1 minus 1 as it is. Note that this is not in the index. So we have to prove that this is divisible by 7. Now, 2 raised to 3 into k plus 1 minus 1 is 2 raised to 3k into 2 cube, laws of indices, minus 1. Now, 2 raised to 3k is 7a plus 1. We have to mention the reason here from 1. Okay. So, 7a plus 1 into 2 cube 8 minus 1. Open the bracket. 56a plus 8 minus 1, that is 56a plus 7. Take 7 common. So 7 into 8a plus 1. Note that a is a natural number. So 8a plus 1 is natural. Multiplied by 7. See, 8a plus 1 need not be multiple of 7. But that natural number multiplied by 7 is definitely multiple of 7 equal to say B, which is a natural number. Actually, I should write here that it is multiple of 7 because of this factor. Okay, so I'll make that change. Just a minute. Because of factor 7 B, that is 7 into 8a plus 1 is multiple of 7, because we have to prove this is multiple of 7. Therefore, P of k plus 1 is true. Now this is correct. P of k plus 1 is true. So you need not write B also, because important thing is this should be multiple of 7, and it is. Now after this I can say that P of k implies P of k plus 1. So step 4, from above steps and by principle of mathematical induction. See, no shortcut. Many students, they just say, so by induction. No. And by principle of mathematical induction. Principle of, basic principle is to write detailed solution if you want full marks. Mathematical induction. P of n is true for all small n belonging to capital N. That is 2 raised to 3n minus 1 is divisible by 7. N is a natural number. Right now. 11th is for homework. It is prove that 2 raised to 4n minus 1 is divisible by 50. Now sum number 12. Prove that 3 raised to n minus 2n minus 1 is divisible by 4. Now it is divisible by 4 if and only if this is multiple of 4. That is 3 raised to n minus 2n minus 1 is 4n. Let this be statement Pn. Now in the first step we verify that result is true for n equal to 1. For n equal to 1 we get 0, which is divisible by 4. So P of 1 is true. Now in the second step we assume that P of k is true. That is 3 raised to k minus 2k minus 1 is 4n, where a is a natural number. Rearrange the terms. So 3 raised to k is what? 2k plus 1 plus 4n. We are going to make use of this while proving P of k plus 1 is true. That will be done in the third step. So in the third step, we prove that P of k plus 1 is true. That is 3 raised to k plus 1 minus 2 into k plus 1. Use of brackets is important. Minus 1 is divisible by 4. Now 3 raised to k plus 1 minus 2 into k plus 1 minus 1. Open the brackets. Laws of indices. 3 raised to k into 3 raised to 1. Now what is 3 raised to k? 2k plus 1 plus 4a. You have to mention the reason from 1. Okay. Now open the brackets. What remains is 4k plus 12. So 4 into k plus 3a. Note that this is multiple of 4 because of this factor 4, and this being a natural number. That is very important, because you can say that 3 is 4 into 3 by 4. So 3 being multiple of 4, it is divisible by 4. No, because it is 4 into not a natural number. But here we are sure that k plus 3a is a natural number. So you have to insist on that. So this is definitely divisible by 4. So p of k plus 1 is true. You may say p of k implies p of k plus 1. So in the fourth step, from above steps, and now you have to write this, not in this fashion, you have to say that, and by the principle of mathematical induction, P of n is true for all small n belonging to capital N. That is 3 raised to n minus 2n minus 1 is divisible by 4. N is a natural number. Write down. Sum number 13. Let me explain first, but please do write the solution after the lecture. Prove by induction 5 plus 5 square plus 5 cube up to 5 raised to n. Clearly, this is sum of the first n terms in geometric progression. Now, please don't say using formula. You have to use method of induction. You have to prove that it is 5 by 4, 5 raised to n minus 1. Let Pn denote the given statement. For n equal to 1, LHS is 5. What is RHS? 5 by 4 into 5 minus 1. Again said, so P of 1 is true. We assume that result is true for n equal to k, where k is a natural number. Naturally, 5 plus 5 square plus 5 cube up to 5 raised to k equal to 5 by 4 into 5 raised to k minus 1. Number 1. You have to say number 1 because we have to make use of this when we assume that when we prove that p of k plus 1 is true. We do that in step number 3. So in step 3, to prove that p of k plus 1 is true, that is to prove 5 plus 5 square up to 5 raised to k plus 1. See, some students, they directly write this and they do not consider this. Actually, even if you write this directly, it is understood that this term is there, but you have to write that. Why? Because sum up to these terms, see the cursor, some of these k terms, we are going to replace it by this. So it is necessary that you write these terms, k terms, one term extra, and that is 5 raised to k plus 1. LHS. Now, for these terms, it is 5 by 4 into 5 raised to k minus 1. This extra term, 5 raised to k plus 1. Now, find LCM and so on. 5 raised to k plus 1 is what? 5 into 5 raised to k. Simple. So, if you simplify, you get 5 by 4 into 5 raised to k plus 1 minus 1, which is right hand side. So, P of k plus 1 is also true. So, from all the above steps and by the principle of mathematical induction, P of n is true for all small n belonging to capital N. That is 5 plus 5 square plus 5 cube up to 5 raised to n is 5 by 4 into 5 raised to n minus 1 for all small n belonging to capital N. 14th, prove by induction cos theta plus I sin theta raised to n equal to cos n theta plus I sin n theta, where I is an imaginary unit, root minus 1. We have done this in the topic complex numbers. This was given by De Moivre. So this is De Moivre's theorem. So we begin with let Pn denote the given statement. In the first step, for n equal to 1, what is LHS? Cos theta plus I sin theta. What is RHS? Same. Actually, I should have written after this. Therefore, P of 1 is true. P of 1 is true. Okay. Now, in the second step, we assume that P of k is true, where k is a natural number. That is, we assume cos theta plus I sin theta raised to k equal to cos k theta plus I sin k theta. Number one, because we have to make use of this. Now third step, we prove that P of k plus 1 is true. That is to prove cos theta plus I sin theta raised to k plus 1 is cos of k plus 1 into theta plus I sin of k plus 1 into theta. LHS equal to laws of indices, raised to k plus 1 means raised to k into this. But cos theta plus I sin theta raised to k from 1 is what? Cos k theta plus I sin k theta. Open the brackets, you get 4 terms. As I equal to root of -1, I square is -1. So which is the real part? Cos k theta cos theta minus sin k theta sin theta. Take I common to get in bracket sin k theta cos theta plus cos k theta sin theta. Now you should know trigonometry. This is expansion of cos of k theta plus theta, and this is expansion of sin of k theta plus theta. So this is cos of k plus 1 into theta plus I sin of k plus 1 into theta, which is nothing but right hand side. So P of k plus 1 is true. You may say that is P of k implies P of k plus 1. So fourth step, from above and by, do not write in this fashion. You have to say by principle of mathematical induction, P of n is true for all small n belonging to capital N. For convenience, we have taken Pn, but original statement, you have to mention that also. That is cos theta plus I sin theta raised to n equal to cos n theta plus I sin n theta. N is a natural number, I equal to root of -1. A good student will mention that this is De Moivre's theorem. So that's it for today.